Okay, anyway, let's get going. Linear algebra and C++. What I want to do today is to look into mostly matrix multiplication as an operation which is absolutely fundamental for scientific applications. We talked about that more than once. The first assignment had, or second assignment had, some aspect of matrix operations in it. But what I want to focus on today mostly is not the matrix multiplication itself, but more the interaction between software and hardware. How can we, and how do we have to take advantage of the hardware architecture modern machines expose? We talked about memory hierarchies, caching that is implemented in these modern architectures. And as we will see, if we take advantage of the way the hardware operates in our code, we can achieve significant performance benefits. If we don't take advantage of the hardware, well, the performance is just as bad as it can get. And I hope to show you some examples and to show you what we need to watch out for. But first, before we start looking into C++, as always, I want to look into some mathematical background, just to put us all on the same page. Really just as a formal introduction of the topic of linear algebra. So let's define a term the mathematicians call a vector space, which is a set V of elements that are called vectors. Please don't confuse these vectors with standard vector. They have nothing in common. Well, very little in common. And I still believe that calling standard vector is just a historical accident and has nothing to do with the mathematical vectors we are talking about here. And these elements have to satisfy the following axioms. Well, the addition has to be commutative. If you have two vectors, it doesn't matter in what sequence you add them. It has to be associative, so it doesn't matter again in what sequence you are adding them. There exists a V and a unique vector 0, which is the idempotent element of that vector space, such that if you add 0 to any vector, you get the same vector out. And there is for every vector x in V, there is a corresponding vector minus x, such that when you add the two, you get the 0 element. For every pair A and x, where A is a scalar and x is a vector, the following two axioms have to be true. Multiplication by scalars has to be associative, so it doesn't matter whether you first multiply the scalar with a vector and then a second scalar, or first the scalars and only afterwards the multiplication with a vector, you will get the same result. And if you multiply a vector with 1, well, obviously you get 1. Last but not least, multiplication by scalars has to be distributive. So the usual distribution laws should apply for scalars and for vectors. So when you multiply with a vector, the distribution laws should hold as well. Very formal definition of a vector space. So let's have a look. The math guys call this an additive group. So in case you are into abstract algebra concepts, this is an additive group with an idempotent element of 0 and an invertive element of -1. Just to make it a bit more practical, some examples. For instance, all set of integer numbers form a vector space. All set of complex numbers form a vector space. The set of all polynomials form a vector space. And last but not least, as a last example, if you look at all n tuples of rational numbers, of real numbers, you get a vector space as well. And that is exactly what we are interested in. Because scientific computing operates on vector spaces of real numbers, essentially matrices of real numbers. And that's where the connection to linear algebra comes from. So how do we represent a vector space on the computer? If we go back 50 years or even longer, Yeah, Fortran, when was Fortran created? In the 50s, 1950s, late 1950s. In those bad old days, vectors were represented by simply arrays. So you have an array, and that's your vector. And you had some Fortran syntax where you said, oh, x and y are real arrays of size n, and you had some functions predefined, sexpy for instance, which does nothing more than multiply all elements of x with a scalar alpha and produce a result in y. The bad thing is that if you were doing the same with double precision floating point numbers, well, you had to use a different function, dexpy. But in the end, it was doing the same thing. Under the hood, these functions essentially just were doing a loop and were multiplying each of the elements of the input vector with the given coefficient and stored the result in the vector. That plus is wrong, so it should be just an assignment here. I will fix that after the lecture. Okay, so what about vector spaces in C++? How do we represent a vector space in C++? Even if Fortran gave us a very clumsy interface to work with arrays or with matrices, or perhaps just because of the clumsiness, it is a very efficient way of implementing things. For a long time, Fortran was the golden standard of linear algebra, and probably still is. A first article I read in 1995, I believe, where some guy came up with some special technique which is called template metaprogramming in C++, and he proved that he can achieve the same performance or even outperform Fortran for linear algebra operations by applying that technique, and that caused sort of an uproar in the community. How could it be that anything is faster than Fortran? Well, C++ can be faster than Fortran if you do it correctly. So let's have a look at what options do we have to represent a vector or a matrix in C++. Well, simplest case, you just create an array, double xn. But the problem here is that this is not dynamically sizable, at least not in a general sense. You can allocate it on a stack, and some compilers support some extension that you actually n can be a variable, but that limits the size of the thing you can allocate because that would be put on the stack, which is not a good thing. You don't want to put a gigabyte of data onto the stack because that would crash your system. The other option certainly is to allocate the memory dynamically just by using malloc and say, okay, I need n elements of size of double, and I get a pointer back to that array. But that moves us into memory management hell, as we know, because raw pointers is a bad thing. I actually promised not to show you even that pointers exist in C++. Here we go. The problem here is that at some point you have to deallocate that memory. You have to give it back to the operating system. So you have to call free on the pointer you got back. And if X is used pervasively all over the place in your code, you don't know which of the places should actually release the code and give it back to the operating system. So we don't want to do that. Well, let's use a standard vector of size n, which is almost good because we don't have to worry about memory management anymore. But the interface of a vector is very limited and not conforming to what a mathematical vector actually expects. Right? It just gives you access to the elements. You can't really multiply two vectors and so on. So what we will do, and what you already have seen in the assignment, we will create our own type, which we call vector, which has exactly the interface we want. Okay, great. What about matrices? Well, you could do a double array. Again, the same problem, not dynamically sizable, or only in a very limited sense. Not an option. We could do a double pointer and allocate it. Well, if you do that, you can very easily get into a situation where you have the worst possible performance if you don't know what you're doing. Because a double pointer means that you have a pointer to an array of pointers where each of those elements in that array of pointers refer to some separate memory. So very easy to get bad performance. Well, why not use a vector of vectors? After all, we said whenever you don't know what data structure to use a vector. Well, use a vector of vectors. But this is not a matrix. and not a 2D data structure at all. Actually, it's not an array, because you have a vector, which each element is a vector. So you have, again, separate memory regions for each of the rows or for each of the columns in your 2D array, which is, again, not what we really want. It's difficult to work with in that way. So again, what we will do, we create a data structure we call matrix, and we can initialize it with the size we need, and it does the magic for us, and it exposes the correct interface for our vector space. Okay, so what we essentially done here, what we've done is to start from first principles and say, okay, we want to build an abstraction that gives us a simple representation of the thing we want to move from the real world into our code. For the domain of scientific computing. And obviously in scientific computing, the domain abstractions are matrices and vectors mostly. So we create the programming abstractions, the matrix type and the vector type, that enable the encapsulation of the data, combine it with the functions we need, give us the interface we need, but hide all the implementation details. So a perfect example of building abstractions in C++, or in any object-oriented language, by the way. Why C++? Again, the question comes up. Couldn't we do that in Java? Yeah, sure, we could do that in Java. But the benefit of C++ is that we have both. We have low-level unadulterated performance and high-level abstractions. And that's, by the way, the only language that gives us both at the same time. Java gives you the nice abstractions, but not the performance. Well, some people claim that Java is faster than C++. I don't believe that, but you get the point. Okay, so what about our rule to use standard vector for any representation of data we need? So if we want to implement our own matrix or vector class, we want to store our data in a vector, because that is kind of the data structure of choice. But what we will do, we will use a vector as an internal representation of our vector, or of mathematical vector, or vector space vector, or matrix. But we will build our own interface on top of that, so that the user doesn't even notice that a vector, standard vector is used under the hood. And this is very important, because as I said, hardware and software have to interact in a certain way. And if you don't do that, you just destroy your performance of your program just to begin with. If you were storing a vector from a vector space in a list, well, you would be doomed. Nothing would work anymore. So we will look into this interaction between the hardware and software in more detail now. Let's start with some linear algebra operations. In addition to the operations, the vector space itself defines as axioms. One of the fundamental operations in linear algebra is the vector dot product. Nothing fancy. Essentially, you have two vectors, x and y. Both have the same size. And the dot product of these two vectors is defined as the per element multiplication and summing up all the multiplication results. And that gives you a single value which represents the dot product. The code is trivial. Well, as you already can see, we have to, let's say we represent it with a standard vector here in this case. All we do is we have a simple loop that multiplies the corresponding elements of the two input vectors and sums up the result in an additional variable, which gives us the vector dot product. Easy. What about a matrix vector multiplication? A matrix is essentially just a set of vectors, right? If you look at it and think, okay, each row in that matrix is a separate vector, and we want to multiply that with another vector b, well, then it's kind of obvious what a matrix vector multiplication means in terms of operations necessary for that. Well, the result is obviously a vector that holds the dot products of every row with the vector b. So we get a vector where each of the elements is a dot product of one of those rows multiplied with a vector b. Other operations on matrices, just a very quick rundown. So it's nothing too complicated. Let's say we have a 2 by 2 matrix with 4 elements. Then if you add two of those matrices. Adding matrices is just the per element addition of the two matrices. Subtracting is obviously, well, just subtracting per element wise. We will look into matrix multiplication in a minute, but another operation that is interesting and we will touch on this time, this lecture, is matrix transposition, which essentially really just means that you flip the rows and the columns of that particular matrix. So theoretically, just from the standpoint of what is matrix multiplication, each element of the resulting matrix C, Cij, which is one element of the matrix, is defined by the vector product of one of the rows with one of the columns of your two matrices. Essentially, the resulting matrix C is the set of all dot products of all combinations of all rows with all columns of the second matrix. Again, dot product. So a dot product is kind of the underlying most important operation we want to do here. Matrix transpose, as I said, essentially just flips rows and columns. So you can think of it, if you have a square matrix, that you flip it along the diagonal of the matrix. As an example, you see that you just flip the elements on the main matrix, on the main diagonal. If the matrix is non-square, then you flip the rows and the columns. So stuff you already know. I just wanted to quickly introduce that or talk about that so that we're on the same page. So I don't think there are any questions so far. We all have seen matrices in algebra, so yeah, if you have questions, let me know. I can certainly elaborate on things. Okay, now things get a bit more interesting. How do we represent matrices in computers in general? How do we do that? Well, we have two issues to solve. First, we have to find the proper interface we want to use to expose to the user. What is the interface? What is the functionality a matrix should expose, a matrix type should expose to the user in order to be usable? And the second part is, how do we implement all of this? And obviously, we want to hide the implementation from the user. The user doesn't care as long as the interface is correct. And there are certainly trade-offs between the two, because in different domains, you might have different criteria you want to decide on. We in high-performance computing, our criteria is performance. So we will build an interface that allows for best possible performance of the operations. In other cases, you have safety requirements. You have the requirement that it has to be absolutely easy to use, or it has to be standard compliant, or there are many other criteria that might apply. But we will focus on the performance part of that, because that is the most important thing for us. In other words, if you look at the matrix multiplication, what might be a nice way of writing a matrix multiplication, if we just think about this formula again, it's three loops, where the outer loop goes over all rows of the first matrix, the next loop goes over all columns of the second matrix, and the inner loop does the dot product for the combination of the current row and the current column of A and B. And C is the sum of all of those operations. So this is what a trivial, straightforward implementation of the matrix multiplication algorithm looks like. So we get a sum. Each element is a sum of the dot product for the corresponding rows. So the inner one is a dot product, and these two are there to go over the rows and the columns of the two matrices. No problem so far. The other nice thing, as you can see, I defined the type, three instances of type matrix, and I defined the sizes I want to have for those matrices in the constructor. So I have, at construction time, I know I can define how large these matrices are, and things will just work fine. So what we have is, we want to multiply two matrices, A and B. Please note that the number of columns in A has to correspond to the number of rows in B, obviously, because we want to do a dot product, and for the dot product, these two things have to have the same size, otherwise dot product doesn't work. And the result is stored in a two-dimensional, notionally two-dimensional data structure. Or conceptually two-dimensional thing. So what we need is a 2D data structure under the hood we want to use to store matrices. And that's what I introduced in the beginning. We have to find a way to expose a interface that gives us the illusion that we actually are dealing with a two-dimensional thing, right? We pass two indices to it. So we have a matrix which is a doubly indexed set. We use a doubly indexed accessor to get to the element ij, and we want to store all of that in a doubly indexed data structure under the hood. Somewhere in memory we have to store these things in a certain way, and we have to ensure that we A, get the semantics right, and B, get the interface right, so that things match. And I want to talk about some details how that can be done now. You might know, and you might be aware of that, you are certainly aware of that, that memory in modern computers is not two-dimensional. Memory is a linear thing. We have one address space where the numbers go from 0 to the maximum number of available bytes, and that's it. So you have some linear collection of bytes we have to use to represent our two-dimensional data structure in certain ways. Memory is contiguous. Everybody's aware of that. But we want to use a doubly indexed accessor. So how do these things actually combine, and how do we get from two indices to a single index that allows us to find the correct address in one-dimensional space? So we have to somehow create a one memory address for one element we want to access in our 2D data structure. Okay, so we have several options to represent a 2D structure in memory, and I already alluded to some, but let's have a look at that a bit more closely. We have to somehow translate the double index to a single address. Well, if we have that double pointer I mentioned before, right? If you have a pointer and somehow magically created a data structure that allows us to store a double indexed thing, then we can use storage ij to access one of the elements directly. And the compiler will do the mapping from ij to the correct address for us. So we use the outer pointer to get the inner pointer. So storage I is a pointer, and we use that as a reference to the array that has the corresponding j element. So we can look up the element from the inner pointer we get from storage I. Same thing if you have a double vector, right? If you have this, we could write it this way and we would get the right element. So again, we look up the inner vector from the outer one. So if you kind of think of having parentheses around the first storage I, you get the vector, the inner vector, and then you use j to index the inner vector. Would work. But as I said, these two representations of memory, the double pointer or vector, is really not what we want to do, because there are many disadvantages associated with it, not the least performance. Performance is probably the biggest problem here. And the way you would have to deal with a double pointer is really not pleasant in C or in C++. Okay, so what can we do? Well, first lecture, first sentence I said, whenever you don't know what to do, just use a vector. Here we go. So let's store our matrix in a single vector of doubles, and we address one element in that vector by k, but now we have the problem that we somehow have to compute the correct k, because all we get is I and j, but we have to somehow get to the k that refers to the element inside that that vector of doubles. Okay, so let's have a look at that. So what about if we store the rows of our matrix in a way that they are consecutive in memory in the linear address space? So let's say that's the first row starts at 0 in our vector of doubles, and the second row starts a bit later. So in the end, you kind of goes through the matrix row by row and concatenate the rows and store them in one giant 1D array in memory. So we have, on one hand, we have a matrix of this size. On the other hand, underneath, we have a vector of doubles that has a size m by n, because it has to hold all the elements. How do we map that? Well, C00 and C01 are the first two elements in our matrix, and those correspond obviously to the first elements in our one-dimensional array. If we look at this element, which is the first element in the second row, our element probably is at the position n, where n is the size of the number of columns, right? Then we can address this. So we have to somehow find a way to compute n, or the index, into our VC vector from I and j. So we have Cij. If we assume that we store our matrix in a row-wise manner, so we concatenate the rows, then our index will grow fastest along a row, obviously, right? This will be 0, 1, 2, 3, and so on. So it will grow along the rows. And that means that we can compute the correct position inside our one-dimensional array by using this formula. Just multiply I with n, where n is a number of columns, and add j, which gives us exactly what we need. For instance, this element would be C012, 01234, so it would be C24. I is 2, so we multiply with a number of columns, which gives us essentially the number of elements in the first two rows, and we add the 4 and get exactly to the element we want. Works, great. But now that we look at that, we actually realize, hey, we could do it the other way around, right? We could store things column-wise. We could say, okay, why do we have to do it row-wise? We could just concatenate the columns and get to the same mapping, or a similar mapping into one-dimensional space. So if we let the index increment fastest along the column, then we get a different formula. This time we have to multiply j with m and add I to get to that element, because we have to go through all the elements until we find this one. So please note, we have the same representation and we have different ways of internal implementing that. So we can abstract the actual internal representation from the user by providing the correct mapping from the two-dimensional space into the one-dimensional index space we need. Okay, so how people call it row major. If you do a row-oriented way of representing memory. And in this case, we write Cij, and under the hood, we multiply it this way. And when we do the column major data layout, we still have the same way of accessing our elements, absolutely same way. But internally, we just find a different element in our one-dimensional data structure to represent the element we need. Okay, so what we need is a matrix type that gives us both things, a two-dimensional accessor and some transparent translation to the underlying one-dimensional accessor in the type. So let's have a look how that looks like. Well, one way would be to use a macro, right? Those C zealots amongst us would say, hey, let's use a macro. Cij, and then we just replace it with this construct. But hey, it doesn't work. Why doesn't it work? Because we don't know what n is. And if you had three matrices of different sizes, we couldn't use that macro anymore. So we would have to funnel in the size of and that would destroy our nice abstraction. So preprocessor is not an option here, and preprocessor is seldom a good option, by the way. So whenever you want to start playing these games, think again, use an inline function. It works much better in most cases. But anyway, okay, let's create such a type. It will be a regular type. In the definition we introduced in the beginning. So it's a type matrix, and it has three data members. it has our storage where we want to store the data for the matrix. And we have to remember how large that matrix actually is, right? We have to remember that we have a certain number of rows and a certain number of columns. And then the whole thing is completely self-contained and represents a particular matrix. What we also need is a set of constructors. Well, the first constructor only gets the sizes and initializes our members to the correct things. So it stores m and n in the num rows and num columns. And storage m by n initializes the vector and creates a vector that is filled with that many zeros you specify there. The other constructor, in addition, allows us to provide an initial value for all elements. No surprise there. Just in case you want to fill it with ones or with twos or whatever, you can use a second constructor. The interesting part here is the accessor. And the way we implement it is using the operator parentheses. So it's a strange syntax you might have seen already, but let's explain what that does. Operator parentheses is used whenever an instance of that type is used in a context where it has parentheses right afterwards. So which gives us exactly what we want, right? If you say matrix A and M, then I can say A, I, J, and refer to the i's and j's element. And since this is an instance of the type matrix and it's used with parentheses right afterwards, so kind of as a callable, as if it was invoked as a function, the compiler will find the operator parentheses and will use that instead of in Leo to implement that operation we want. So that gives us the two-dimensional accessor. Well, you might say, why don't we just define the operator brackets? That would allow us to write it this way. That would be much more kind of approachable for us, right? Because normally we use the bracket operator for indexing into arrays. Well, the reason is up until C++23, I believe, C++ didn't allow to have more than one argument for the bracket operator. It was only lifted recently, that restriction. So nowadays we could actually write operator bracket here and would get the same result. But just for whatever reason, I decided to use the operator, the function operator here in this case. As you can see, what the operator does, it takes the two indices and computes the correct index into our one-dimensional array based on the formula we derived. And that's where it needs the members that remember how large that matrix actually is. The second thing, you might say, hey, why do I have two of those operators? And that is another C++ thing I want to introduce here. You see that the difference between that first operator and the second operator is that const keyword that is placed in a very strange place. That const keyword doesn't refer to any variable. It just is in between the header of the function and the body of the function. Well, this is a syntax C++ uses to say, please use this operator if you happen to be invoked on a const object, and use this operator if you happen to be invoked on a non-const object. In other words, this operator allows us to modify the thing it's referring to. That's why it's returning a reference to the current element, which allows us to assign to it actually, right? Because it gives us a reference to that element. And this doesn't allow us to do that. It just gives us a const reference, which does not allow us to assign to a single element. And we don't want for that to work because, well, it's invoked on a const object. So we are not allowed to change the single elements in that object either. Last but not least, just expose the rows and the column numbers for that type so we can refer to it from the outside of the class later on, because these things are private in the class. Any questions about that? fairly straightforward, simple C++ code. But this is mostly the matrix abstraction we will work with. All it gives us is the storage management. It stores the data in a vector of doubles, and it gives us the accessors that allow us to map from a two-dimensional index space to a corresponding one-dimensional index space. Now you might say, hey, the operators actually give us row major memory layout. How do we do a column major memory layout if we want to work with that? Well, we define just operators differently. So we introduce a second type, which we call probably column major matrix, and rename the first one into row major matrix. And the only difference between the two is actually the way the mapping from the two-dimensional index to the one-dimensional index is being done. Note that the interface is the same. I'm using I, J as the two indices. It's just that the two indices are used in a different way under the hood in order to do the mapping onto the one-dimensional array. Okay, so let's go with this. This is our matrix class, and please always, when we use these matrices in the code that is to come, think about that implementation, because this is what it actually is under the hood. Okay. I really assume that you will interrupt me if you have any questions. So if you don't interrupt me, I will assume that everything is clear as sky and I can go on and push on. Okay, from now on, I will assume that our matrices are square, just for simplicity, because that helps writing the code in a more straightforward way. But everything applies to non-square matrices in the same way. So we are interested in performance. So let's do a performance analysis of a matrix multiplication. As that slide says, the algorithm requires n-cubed multiplications, right? Outer loop n, next loop n, inner loop n, and we have one multiplication per loop iteration. So it's n-cubed, n times n multiplications, and n-cubed additions. So the sequential time complexity of a matrix multiplication is O(n) cubed. It's a very bad complexity. So it's a very complicated operation, actually, in terms of time complexity. So luckily, it's very easy to parallelize. But unlucky for us, it's very difficult to parallelize correctly. It's very difficult to parallelize correctly. And people have spent their whole career in coming up with matrix multiplication algorithms that actually gives you something close to peak performance of what the hardware can support. Really, you can spend a lifetime to do that. And we will see some of the reasons for that in a minute. But what else can we do in terms of performance when we start parallelizing? Just let's conceptually parallelize. Let's say, let's have a look at our code, and we will see that the inner loop is actually independent from each other thing. So we can outsource all inner loops to separate processors. So if we have n matrix elements, we have to perform n dot products, which is what the innermost thing is. So let's move one dot product to each of the processors. So let's say we have n processors. That gives us a O(n) squared time complexity, because now we can distribute the inner loop, and we have only n squared complexity in terms of time, not in terms of operations. They stay the same, but in terms of time required, because each instance of the inner loop is independent of any of the others and can be done on separate processes, if we were able to do it. We can do even better. If we have n squared number of processors, we can do it in O(n) linear time, with linear time complexity, because all we have to do is make one processor responsible for one of the result values. And since we have n squared result values in n squared processors, it takes only O(n) time to do the computation. And both of those cases are cost optimal, because in the end, the complexity is the same for both in terms of general effort, right? We can do even better. What we can do, if we have n cubed processors, we in theory could achieve O log n performance, which is a very good time complexity. But this is not cost optimal anymore because the number of operations is much smaller than the number of the effort we have to invest. We have to invest O log n times n to the power of 3 operations overall in the system. And now you might ask, hey, how do I do that? And where do I get the performance for the last parallelization step from? Well, you just do a tree-based addition, right? You have 8 elements, 3 processes in this case, and you can do a multiplication step by step and distribute the operations in a tree-based fashion. And since this is a tree, the complexity is log n, obviously, right? So just to give you some theoretical bound of what is in theory possible. Well, nobody is able to do that because you can't just distribute one floating point operation to one processor and have a million processors doing that. The overhead of managing a million processors to do one floating point operation each is so immense that overall the performance wouldn't be the best possible anymore. But in theory, this is what is our limit. So O log n is a lower bound for parallel matrix multiplication. And if we had a midterm, this would be a question. What is a computational complexity? What is a lower bound for time complexity for matrix multiplication? So you can remember that. It's O log n. Okay. Since we talk about timing and benchmarking, let's do that a bit more thoroughly. Besides the fact that we always want to measure who has a bigger one and who can run faster, we have to find a criteria we use for performance and how to measure it. It's even that linear system solutions, that linear algebra is one of the major algorithms that is currently used to assess the performance of the biggest computers we have in the world. So these top 500 machines, right, there's a top 500 list that is maintained twice a year, and whenever somebody comes up with a big machine, they try to get on that list to prove that their machine is a bigger one. And in order to measure that, they actually do giant matrix multiplications, nothing else. And then they say, okay, this matrix had this amount of elements, we had to do this amount of operations, it took us that amount of time, and that gives us a measure which is flop per second, floating point operations per second. If somebody talks about flops per second, call them an idiot, okay? Because that S stands for per second, even if there is no slash in between. So flops always stands for floating point operations per second. So it's never floating point operation per second, right? So that's why. And that is a Linpex suite which essentially does n to the power of 3 multiplications and measures how long does it take to do that on a machine that has 1 million processors or whatever. Okay. The possibly most wrong way to assess performance of computers, because it measures only one way of doing computing. But hey, that's what people do. How do we do that? Well, the simplest case, if we want to figure out how long does it take to run a command on the command line, we just use the time command, prefix it to our executable, and it will spit out 3 times: the real time, the user time, and the system time. So real time is the wall clock time, how long did it take? User and system is the amount of time that process took running in user mode and in kernel mode. So if you had an operating system class, you know what I'm talking about. We are interested in the how long does it take, right? And measuring the whole execution is probably not what we want, because we are really interested only in figuring out how long does it take to do our matrix multiplication. So that's why back then in the day I introduced that timer class. You used it in your homework, I believe, just to remind you. It's a class that has 3 functions that are interesting for us: start, stop, and elapsed. And it gives you the time elapsed between the last call to start and the last call to stop. Nothing else. So very nice. It's exactly what we need. Okay, so let's have a look at our matrix multiplication algorithm. What are we dealing with? Well, we are dealing with, if we assume that the loops don't take up any time. So let's just move them out of the picture. All we are dealing with is multiplication and addition. Also, we deal with how much data was actually moved from main memory into the processor and how many floating point operations have we achieved in the end, because that is the number we are interested in. So let's write some code which loops over various matrix sizes from 8 by 8 to 1024 by 1024. And for each of those iterations, it instantiates two matrices, A and B, somehow initializes them, doesn't matter. And then it creates a timer, starts the timer, does the matrix multiplication, stops the timer, and prints the elapsed time. And here we get to a phenomena that you probably observed in your assignment. You start measuring things, and it tells you that it took 0 seconds, right? I asked you to discuss that on Discord. Nobody actually did that. So I assume that everybody figured out for themselves what is the reason for that. What came you up with? What was the reason for this? That you measured things and suddenly it didn't take any time anymore. Right? Before, in debug mode, it did something. In release mode, you couldn't measure it anymore. Remember that one? Okay. Well, there are two reasons for this. The first reason is the amount of work is too small in order to be more than a millisecond. The second reason is, in your case, the compiler was smart enough to see that you're not doing anything with the result you were computing and were optimizing the whole thing away. We're just saying, okay, the user was doing some complicated computation, assigned it to some variable, which is good, and then suddenly the variable is not used anywhere. So what the hell is he doing? Let's get rid of that code. I don't need it. So what you were measuring was actually not what you were intending to measure, your code, but you were measuring what the compiler left over after optimizing away everything you were actually writing. Because compilers are very smart today. They figure out if code that is producing something, a result is not used anywhere, or the compiler can prove to itself that it's not used anywhere. And that's why you got 0. End of story. As easy as that. What can you do about that? Any idea? Well, the first one is, I will show you how we can overcome the problem that it's actually too little time. But the second one, how do you avoid for the compiler to optimize things away? Very important for benchmarking. The easiest way to do that is to assign the result to a global variable. A variable which lives outside of the scope of your function. You don't use it, but the compiler can't prove anymore that this variable is not used in any other translation unit. So the compiler has to assume that this variable you're assigning is used somewhere else in your program, and it will not optimize away things. Okay? So whenever you run into the issue that your benchmark is suddenly not giving you any timing anymore because the compiler was too eager to get rid of what the compiler thought was your stupidity, assign the result of your computation to a global variable. And if you want to make sure that it's really not optimizing away, make the global variable volatile. Volatile double x, and then inside your code, x equals whatever code you have to do the performance measurement. Okay? That will guarantee that the compiler will not optimize things away. What does volatile keyword mean? It means it tells the compiler, please never optimize that variable into a register and always put back the value into the main memory once you have a new result for it. So it will prevent optimization of things related to this variable. And that's what we want. Okay? So how do we overcome this part? Well, this part, if you look at what we actually measure, right? We have that operator star, which does a matrix multiplication, and it executes that loop, creates a local variable inside that function, which is initialized to 0 and returns that matrix C as a result of that operation. But since we are measuring the whole matrix operation, the multiplication, we measure the whole function. So we not only measure the 3 loops, but we measure the allocation of the memory and the zeroing out of all elements of that matrix, which we don't want. So what we will do, we will separate these two parts into two functions. The matrix multiplication now calls a multiply function, and the multiply function is that bare bone thing we're interested in measuring. So never measure allocation time in your benchmarks. Whenever you allocate memory, move that out of the measurement region. Be sure of that, because that will skew your measurements. And now we can call that multiply function directly without doing the star operation, just for benchmarking purposes, and run it n times. Not once, but 100 times, 1,000 times, 1,000,000 times, depending on how much data, how large our matrices are. And then we can use the elapsed time to actually assess what the real time is. Well, we even could divide it by the number of samples. No, that would give us something less than a millisecond again. So we just measure the execution of 1,000 operations, and that gives us something we can compare with, okay? So just some hints on how to do benchmarking. So this has nothing to do with linear algebra, but it's a common thing you want to do. Okay, so run the loop more than once to get sufficient resolution. Okay, now let's measure this. What does our code produce? Our code produces a graph like this. On the y-axis, we have the gigaflop per second, and on the x-axis, we have the matrix dimensions. So for small matrices and very large matrices. And as we see, this code doesn't perform very well, but it doesn't perform very well uniformly. So no matter what the matrix size is, it gives essentially the same amount of floating point operations per second. Please note, this is in debug mode. So another hint, never run performance measurements in debug mode, because if you just switch to release mode in Visual Studio Code, you will see this. Bang. And now things start looking a bit more as expected, because very small matrices give you better performance than very large matrices. Why is that? Anybody? Why does that code run much faster for very small matrices compared to large matrices? Anybody? Think about architecture. Think about caches. How large are caches? A cache has a limited size. So the large matrix might not fit into the cache anymore. But the small matrices do. And since the small matrices fit in the caches and we do the multiplication more than once, only the first measurement, the first loop of our measurement actually loads things into memory, and all subsequent measurement iterations of our measurement loop work with data that is already in the caches. Well, it fits in there, right? There's nothing else going on, so we don't thrash our caches. So all the matrices are in cache, and the access times to the level 1 cache or level 2 cache are much, much smaller than the access times to the external memory. That explains why this is happening. And starting a certain size, well, we see it flattening off, because then things don't fit into caches anymore, and it doesn't matter anymore, because I have to constantly reload things into the from the main memory as I go. Okay, so caches are much smaller than main memory. So somehow we have to make sure that the data we're using is still in the cache or is already in the cache when we need it. And there are two criteria we can apply and two techniques we can apply to ensure that. The first one is called utilize temporal locality. Temporal locality means I have an algorithm that loads some piece of data into the caches, and the probability that this very same value is needed right afterwards again is very high. So over time, the same stuff is still in the cache what I have loaded into the cache before. So the cache replacement policies in our architecture attempt to keep cached things in the caches as long as possible. So they load things as they go, and only when the cache is full, they start evicting the elements that have not been accessed for the longest time. So you have always the things in the caches that have been accessed recently. And if you have an algorithm that takes advantage of that and reuses things that are already in the caches, you will get that better performance, as we have seen in the previous example. The other thing is spatial locality. And that is what I mentioned several times, that caches in modern architectures operate not on byte level, but on cache line level. That means that when you read 1 byte from the main memory, the architecture will load 64 bytes surrounding that 1 byte into the cache line and will keep the 64 bytes that surround that 1 byte together with that 1 byte in the caches. In other words, when you load one of those bytes and then your algorithm needs the next byte in that is next to the one you needed on the next iteration, the chances are very high that this next byte is already in the caches because that memory operation has already loaded the whole cache line. And that's why it's called spatial locality. It's spatial in the terms of close by, in terms of distance in the memory. And since, again, the caches read contiguous chunk of data, usually 64 bytes. There are other architectures that read more, but x86 and ARM and the common architectures usually use 64 bytes for that. You always get not only what you want when you read something from main memory, but you get 64 surrounding bytes. Okay? So, what can we do with that information? Here's our algorithm we had. So if we look at each of the inner loops of the innermost loop, what does it do? It loads C, ij, it loads A, ik, it loads B, kj, then it multiplies, then it adds things, and then it writes that Cij back to the memory, right? This is what this code is doing. So we have 4 memory operations, 1, 2, 3, 4, 2 floating point operations. In overall 6 operations, if we assume that all of these operations take the same amount of time, let's assume that for now. It's not true, but let's assume that. That means we have about 1/3 floating point operations per iteration. Per cycle, right? 6 operations, 2 of them are floating point operations, so it's 1/3 floating point operations per cycle of processor cycle. If you assume that these operations take 1 cycle, which is probably not true, but for now, let's do that. Okay? So what can we observe? Can we reuse something in this? Can we take advantage of some local, of some temporal locality? So in other words, is there some variable that will be reused on every iteration so that the probability for that variable to be still in the caches is very high? Well, as we will see, yeah, Cij is used on each iteration of the inner loop. So we load it on each step of the inner loop over and over again. So why don't we hoist it? Why don't we just say, okay, let's read that C once in the beginning of the inner loop, then do our dot product and write back the result afterwards. That will essentially tell the compiler, or the compiler will be smart enough to understand that it should keep the variable t in one of its registers. It will not write it back to the main memory. It will just put it in one of its registers, and you're fine. So what we get is we have only 4 operations now, because we can just say, okay, we don't care about that loading of C and storing of C because it's outside of our inner loop. And that means we have already 1/2, 1/2 floating point operations per cycle. 4 operations and 2 floating point operations amongst those, which is an improvement, right? Okay. What else can we do? Let's look at the order of operations. We have that matrix C, and we want to multiply these 2 matrices. So that is the result we need. We need 1 element from here, 1 element from here, and then we go through the 2 matrices and do the vector product for the first combination of the first row and the first column. Then we go to the next row and we do the same thing, right? So you already see that there is some pattern to the madness. Apparently we need to use that thing twice. That's one thing. And the second thing is that is it a good idea to go this way through the memory, or should we go column-wise? So that's a decision we have to make. If we do it for these 4 elements in the matrix, we will see that we actually use 2 rows and 2 columns, but each of them is used twice. How many times do we use them? Well, in order to do these 4 computations, we will need, for these 4 values, we will need only 2 rows and 2 columns. That means that if we, instead of just going one by one through the matrix, but looking at the matrix tile-wise, looking at 4 operations at once, we might be able to convince the compiler to save memory accesses, because in order to compute 4 elements, we need only 2 rows and 2 columns, and not 4 rows and 4 columns, as we were needing so far. So the order of reordering the matrix multiplication operations will save us, because it allows us to reuse things that most likely are still in memory, in the caches. So what we would do, instead of computing 1 element on each iteration, we now compute 2 elements. And that one is wrong. That should be k plus equals 2, obviously, because I'm just going through the index by increment of 2. So I apologize for that. I will fix it. So we do 4 operations. And as you can see, we reuse a lot of those elements. For these 4 things, I can reuse A, I can reuse that A, I can reuse that B, and I can reuse that B. Gives us temporal locality, because things are most likely still in memory. So these things are used twice each. And additionally, which is not shown in the code, we could hoist the 4 C variables out of the inner loop to avoid these memory operations there as well, because it's the same as before. If we do that, we get 4 memory operations and 8 floating point operations per iteration, which gives us 2/3 flops per cycle, which is already twice as good as we started off with. Right? We started with 1/3, 1/3, and now we have 2/3. That's the measurement. So this is when I do tiling on a 2x2 grid, as I showed. This is when I do tiling on a 2x4 grid. This is when I do tiling on a 4x2 grid and 4x4. As you can see, there are limits for the tiling, because in order for things to be kept in the core, you need to have register space. And the cores have only limited amount of registers. So when I try to store 16 intermediate variables, amongst other things, the core can't do that because there's not enough hardware available to store these things. And that's why the performance is not that brilliant. It's still better, but we still get almost the best performance for the 2x2 case. Okay. Yeah, that is the code that does the hoisting, which I mentioned. And if we hoist it additionally, we get, bang, suddenly very good performance. By a factor of 2, right? I said twice as much, twice as many operations per cycle. So you see roughly an increase in a factor of 2 in terms of performance. And now we are getting kind of close to, much closer to the theoretical limit we could achieve. So this is the first thing you have to remember. Always be aware of how the caches work, because that temporal locality is absolutely crucial in many cases. A, because the core can store things in internal registers, or at least leave it in level 1 cache, close to the core, where the access time is only slightly larger than access time to the registers. Okay. Another thing you can do is called block multiplication, block matrix multiplication. As it turns out, you don't have to do the multiplication element-wise, but you can cut out a block of the matrix and matrix multiply it with a similar sized block on the other end, and you still get the correct result, and you get a block in the resulting matrix. So you can increase the amount of data that is actually kept in the caches, because now you not only keep the 2x2 in the registers, but you keep, I don't know, 8x8, 16x16, or even 64x64 doubles very close to the core. Here's the math. I'm not going to talk about that too detailed. So if you multiply 2 matrices, you can do it blockwise, and you get the correct result in the end. You can follow that just for yourself. There's also an algorithm which is called Strassen's algorithm, which allows you, if you do that blocking recursively, you get a much better time complexity and even computational complexity out of that, but just as an aside. So if we do blocking, we increase temporal locality again. We want to compute this block in the matrix. This is now not one element, but I don't know, 64 by 64 elements. And we need to go over these 4 matrices and these 4 matrices and do the normal matrix multiplication on the block by block basis, which will amortize the n cubed work in a nice way. Okay, so just for your interest, this is a code which now has suddenly not 3 loops but 6 loops, and the outer loop goes over the blocks, and the inner loop does the matrix multiplication for each of those blocks. So the inner loop works with the blocks. You see it goes from k to k plus block size, and the outer loop iterates over these blocks of the matrices. We get better performance, the green line. Why do we get better performance? Why is that green line, especially for larger matrix sizes, beneficial? Why is blocking of matrices beneficial for larger matrix sizes compared to the hoisted one we looked at before, right? That one was the best one, the black one. Any guesses? Well, at least, yeah, please. Again, caches, right? Because you keep it in level 1 cache. You don't work on the whole thing. You work only on one block of the matrix or on 3 small blocks on a matrix. And we have seen that for very small matrices, the performance is always better than for large matrices. So if we do our overall operation on small matrices, because that's what we do, the probability that these small matrices are still in the caches while we iterate over them is much higher than before. So we can gain a lot of performance, especially for larger matrices, with that block hoisted thing, with that algorithm that uses 6 for loops. By the way, if you want to do a really performant matrix multiplication algorithm, you need at least 12 nested loops. So we can go further and further. We can make it much more complicated, but I will not go there here. Okay, the other thing I want to mention is if we look at how do we do the computation. If we compute this element, we read this element and we read this element, but what else is pulled into the caches, right? When I read this element, the 64 surrounding bytes are being loaded into the caches. So we get at least one to a couple of more elements that are next to the one we're interested in the caches. But this doesn't happen here because it will load this element into the cache while we need this element. So what happens if we actually, before doing the multiplication, transpose this matrix? Or optionally make this matrix column major. Multiply a row major with a column major matrix. What happens in this case is that now both will load their neighboring element in the cache so that the next operation for the next element will already find the thing we need in the level 1 caches. But for that, we need to apply an additional step. We need to transpose that other matrix, which certainly imposes our performance. So if we just do a transposition, here, we get about this performance, the red line. So we transpose it, then we apply our algorithms, and it's not as good as before because, well, we had to do an additional copy step to transpose our matrix. And the larger the matrix, the more expensive it is, and so on and so on. So that hurts our performance. But it could be beneficial if you have a system of linear equations where the matrix you're multiplying with doesn't change. Because in that case, you can transpose that once and reapply it on each iteration of your code and can take advantage of that. But if you not only do the transposition, but you hoist it in addition, then suddenly you get very good performance again. So just to give you some thought of how can I optimize my code? How can I get better performance out of what I'm doing? Well, the thing is always think about what is a memory doing, because a memory is always the culprit when performance is bad. Bad performance, memory. It's a sure bet. There is no other answer to bad performance. Okay, so let's recap. We have to be aware of locality, so we have to write the software in a way that the hardware can leverage it, or that the software can leverage the hardware. We want to use registers in the core to take advantage of temporal locality. So load things into the core, into the registers of the core as much as possible, but not overdo it, because you can't overspill. It's called register spilling. That if you load too many things in the core, in the registers, and then suddenly you don't have any effect anymore. But hoisting and blocking are two techniques that allow us to take benefit at least of caches. And special locality, well, we can do transposition of matrices that gives us spatial locality, because the second matrix will take advantage of the way caches work, because we not go column-wise through that second matrix anymore, but row-wise, because we have transposed it, and that gives us the benefit of how the caches work. Okay, so some general rules. How do I tune my software? Well, you want to start with a simple code base. The general rule is you can always make a correct program fast, but you can't make a fast program correct. So always start with a simple solution that you can understand, that you can convince yourself it does the right thing. That gives you the baseline, and you can go from there. Various compiler optimizations may help. Enable vectorization, enable release, disable debug mode, things like that. You want to do tiling, but then you have to decide what size should I use for my tiling. You can do blocking. What size do I use for my blocks? What works best for those things? What loop ordering do I use? As we will see in next assignment, there are actually 6 ways of order a loop, right? If you have 3 loops, you can order them 6 ways. You don't have to start with ijk. You can do kij or kji or whatever. It will get the same results. So next assignment will ask you actually to compare these 6 orderings and to find out what is the best one, and tell me why is that the best one. Okay? What about when we add vectorization? We add thread parallelization. What is happening? So many questions. So how do we find the optimal combination of all of those is an open question. And people have come up with methods to find out what's actually going on. Because what will be true in terms of parameters on one architecture on your laptop might not be the optimal solution on a different machine, on a different architecture. Different cache sizes, different number of processors, you name it. So finding the sweet spot is something that requires an exhaustive parameter sweep. So in theory, you have to write a code that goes through all the parameters in all parameter directions and tests out and finds the best way for your case. Usually not really applicable, because that would take it doesn't work that way. But people have still tried to do that, and what they have done, they have written a code which is called Atlas, which stands for Automatically Tuned Linear Algebra Subprograms. And this is a library. When you install it, it actually goes away for 3 hours and does that parameter sweep for you in the background. And then it generates optimal code for your platform. It generates the code. It doesn't change parameters. It just changes the code layout physically. And then you compile the generated code to get best possible performance. So if you're really into high-speed things to the maximum, use Atlas. It's a pain to install because, as I said, it takes several hours to do all of that. And you can constrain it if you want to, but it will take a while. But you will get really best performance for this platform. Now, you can't move that to a different platform and expect good performance. You have to do the same thing again. But it gives you at least something to play with. So people have thought about that. People have tried to find solutions to this problem. Again, the takeaway here is there is no single best possible performance solution, because it depends on so many factors. Nobody understands that actually just from looking at it. You have to try it out. You have to do measurement. And as always in benchmarking, there are 3 things you have to do: measure, measure, and measure. And when you do these 3 things, you will get that good performance on your software. Okay, thank you so much. The lecture on Thursday will be cancelled. I'll see you next Tuesday. Thank you.